Hello everyone, welcome to another session on RCDC. So in our previous session we have seen how to design a beam as per IS456 in RCDC, and I have also understood the design calculation in detail. Today in this session we are going to understand the same beam design as per IS456 along with IS13920 criteria. That means we will be performing a ductile design of beams, and we will understand the design calculations in RCDC. Okay, so I'll just open the previous file, and what I will do, I will unlock the file as it is already a design as per the IS 456 criteria. So I'll just unlock this and I will do the settings again. So I'll just go to settings, and here I will click on general and reinforcement setting. So first of all, I have already explained in the previous session, but still I'm just giving a insight. You can say, let us have a brushed up session on this. So ignore torsion. I am not checking it because I do not want to ignore the torsion. Let us have the torsion and we will understand the design calculations. Now, as we are performing ductile design, so we need to perform the ductile design. So we need to check this option. Okay. So what I will do, I will check this option. Now it is asking whether you want to design the beam as ductile in the ends only, where you can see ductile shear at supports, or you want to design the whole section as a ductile, you can say as per the ductile criteria. So I want the whole section to be designed as the ductile design criteria. So I'll just click on this at all sections. Flange beam, like the T beam and L beam, as we have already discussed that this T beam and L beam are not efficient at the when you can say load reversal is there. We don't know at which section we will be having tension, at which section we will be having compression, because T sections and L sections are effective when there is a sagging moment, correct? So at the top there is a compression, okay, then only the T or L will be effective. So generally in case of you can say gravity loads, only at the midspan we will be getting it. In case of seismic load, the load reversal will be there, so we don't know actually what will be the exact I can say condition. So what we are doing, we are not taking the advantage of this T and L, you can say flange. Okay, so we are designing the beam as a rectangular beam, so that's why I'm not taking it as a flange beam. Bending and axial force, this is basically as per this criteria. If you see here, we have a criteria in IS13920. So you can see here that requirements of section shall, in case of beams, okay, requirements of section shall apply to beams resisting earthquake induced effects in which the factored axial compressive stress, okay, factored axial compressive stress does not exceed 0.08 FCK. Beams in which the factored axial stress exceeds 0.08 FCK shall be designed as per the requirements of 7. Okay, so when the beam is subjected to axial load, which is very rare case, it can be, obviously it can be. So if it is subjected to axial load and the stress exceeds 0.08 FCK, in that case those beams should be designed as per the section 7. And section 7 is talking about, if you see here, we all know section 7 is talking about column and inclined members actually. So in that case, so you have to design the beam as a column, okay, taking the axial load on the beam. So that criteria I will not select now, okay, I will not check it now. I will just leave it, because when we'll be explaining the column design, then I will discuss this. Okay. Detailing part, now I will keep it best fit, because when we'll be seeing the drawings, then we will I can say do trial and error among these options. I have already discussed what these options are. As of now, in this case, we will be keeping the best fit only. Minimum percentage of steel. So earlier we have calculated for, as per IS456 criteria, that the formula was 0.85 by Fy. This is the minimum ratio, and multiplied by B into D multiplied by 100%. So it was something like this, and we were getting, no, sorry, I think sorry, I have written it wrong. So it is 0.85 by Fy. This is my PT actually, I guess. Yes, this is my PT. Okay, this is my PT that we had. So 0.85 by Fy, we got 0.17%, right? Let me just check, or it is the ratio. I forgot actually. 0.85 divided by 500. Okay, so this is the ratio. Then we multiply this with 100%. Then we will be getting this 0.17%. Correct? So PT is this 100%. Correct? Now, in our current case, we are designing it as a ductile beam. The beam says a ductile beam. So we need to consider this criteria, which is about 6.2.1. B, it is saying that minimum longitudinal steel ratio rho mean required at any phase at any section. Actually, it should be, this is the ratio, okay, 0.24 root FCK by Fy. So if we do, in our case, it is M25 grade of concrete and Fe 500 grade of steel. Okay, so if you do the calculation, 0.24 multiplied by root FCK by Fy, how much we are getting? So just calculate this. 0.24 multiplied by root FCK by Fy. So we are getting a value of 2.4 multiplied by 10 power minus 3. If I multiply this with 100, so we are getting 0.24%. Okay, so I'll just put it here. I'll put it here, that 0.24% is my minimum percentage of steel. So minimum percentage of steel, this is not only the criteria, there will be another two sections, which is 6.2.3 where it says that at the bottom of the beam, at least half of the AST that you have provided at the top should be given actually. So you can see longitudinal steel on bottom face of beam framing into a column shall be at least half of the steel on top face at the same section. So at the end of the beam, whatever steel you have provided at the top, half of it should be, at least half of it should be provided at the bottom also. And again, longitudinal steel in beams at any section actually on top or bottom face shall be at least 1/4 of the longitudinal steel provided at the top face. So at the end of the beam, whatever reinforcement area you have provided at the top face, 1/4 of this area should at least be provided at the any section of the beam. Okay, so these three criterias will be checking. So the value that we have given is this one. The other two will be checked by the software. That's not an issue. I will show you how it is checking. Maximum reinforcement ratio. So for that we have this 6.2.2. Maximum longitudinal steel ratio rho max provided at any face of the section is 0.025. So this is the ratio. If I multiply this with 100, 0.025 multiplied by 100, so it will be 2.5%. Correct? Yes, 2.5%. So I'll just put it here as 2.5%. Okay, nominal steel we will keep 0.24 only. We do not want to provide any steel less than this. Okay, so 0.24. Crack width check, I will not check it now, we will see it later. So this is my grade of concrete, grade of steel, you can say grade of steel for the shear design, clear cover 25 mm, maximum aggregate size 20 mm. Bar dia we have selected 8, 10, 12, 16 and 20. For main bars 12 to 20, this is the limit we have selected. You can increase it also. Minimum bar dia should be 12 mm as per, you can see. Beam shall have at least two minimum 12 mm dia bars. Okay, so I have selected minimum dia bar as 12 mm. Shear bars 8 to 10, and for the side face reinforcement I have selected 12 to 16. Correct? Minimum spacing, we know that we cannot provide a spacing less than 100 mm. So greater than 100 mm as per ductile design criteria at any section actually. So if you see in this end area where we will be providing closely spaced stirrups, we have three criteria: D by 4, this is actually 6 times dB after the new correction of or guess amendment, and this is 100 mm. So you cannot provide anything greater than 100 mm. So what I will do, I will keep it as minimum value as 75 mm, less than 75 mm, 100 mm providing. Maximum spacing I kept it 300 mm, doesn't matter because it will be checking the code, and as per the code criteria it will be providing it, because here you can see for this area where we will be providing higher spacing, so it should be less than effective depth by 2. Okay, so I will keep it 300 mm. So based on the you can say effective depth value, it will be providing. Spacing round off, I will keep it 25 mm. So if you want to increase, it will increase with multiples of 25. Okay, and I will click on OK. I'll go to settings now. I will go to rebar curtailment. So rebar curtailment, we have already seen this. If you want to brush up the things, so I will just show you here. Top steel curtailment location and continuous end support and continuous support. Okay, top steel curtailment location. So if you see, if I go to SP34 and this is my top steel curtailment location. Okay, this A, it says distance, let me just zoom it a bit. Distance to point of inflection plus encouraged length, but not less than ln/4. Okay, not less than ln/4. So I kept it as ln/4. Continuous support, at continuous support also how much it is, you can see this is the same A, so ln/4. And then bottom steel curtailment location mid span. So it says, you can see basically bottom steel you will not get it here. Okay, let me see. Bottom steel curtailment location L1, is there any value of L1? Actually it is not given here, so I will keep it as ln/4 only. I have not found actually where this L1 is given. If you find, please do let me know. So what I'm doing, instead of providing a lesser value, I am going a bit higher, conservative approach. I'm keeping it like this, so it is also ln/4 I kept. I didn't find this L1 value. If you find, please do let me know in the comment so that I can also update. Okay, so I am keeping it as ln/4 only. See this end support, I am keeping it as L/4. Now mid span, actually what it is talking about at mid span. So when we see at the mid span, we cannot see this particular picture. We have to see the picture for the general detailing, not for ductile detailing. Okay, so let me show you, like if there is a extra bottom reinforcement to be provided at the mid span, how the curtailment should be given. Let me go to beam section. Beams, where it is, yeah. So this is, yeah. So if you see this image here, we have an extra bottom, and it is talking about this particular length, which is 0.15 L1. L1 is nothing but the total. L1 is nothing but the total span. So here it is saying L1. I don't know whether the same L1 is mentioned in the ductile design also. I don't think so. Okay, no problem. So here it is saying that 0.1 L1 at the ends and 0.15 L1 at the continuous support. Okay, so this is about this bottom mid span curtailment. Okay, so how much you need to keep from the center of the column. So what I will do, I will keep it as, if you see 0.15 L1 and L/6. So if you do 1/6, how much you are getting? 1/6 you are getting 0.16, and it is asking about around 0.15. okay, and if it is 0.1, so you can keep it as 0.15 only. What I will do, I will not change it. I will keep it as midspan 0.16, because as we are doing ductile design, so obviously we'll be providing some you can say enough end reinforcement also. So what I will do, I will keep it as same as this L/6 for as per the continuous condition. And support we have already seen in the ductile criteria. Okay, and support, so I am keeping it as 0.25 L only, that means L/4. And continuous support, okay, it is also given continuous support. Continuous support, if you see here, bottom steel continuous support, it is asking 0.15 L1. okay, 0.15 L1. so that means I can keep it as, I don't know, there is something wrong here, because what is 1/3? 1/3, 0.3. This value, it is 0.1 L1, it is 0.15 L1. So we don't have any option for this end. For continuous support, okay, 0.16 conservatively we can provide. So I'll just provide for continuous support, I will provide L/6, correct? And for mid span also, we have provided L/6 continuous support. Let me see, I think I am just messing up somewhere. Bottom steel mid span, okay, mid span we have already cleared, we have provided 0.15 L1 in both ends, fine. And support, now we need to go to this criteria actually, and that's why I got confused. I need to go to this criteria, which is for beams in the ductile design criteria, okay, ductile detailing criteria. So I will, that's the problem, I hardly remember the page number, and then again I have to find it like this. Yeah, so yeah, here it is giving L1 and L1. We don't know what is this L1 is, so we are keeping it as A only. Okay, we are keeping it as A only. So let us provide A means L/4. So here at continuous support also L/4, at end support also L/4. I hope now you understood. Okay, if I draw it something like this, what I did, this one I kept as A, this one also I kept as A. And if there is an extra bottom reinforcement, this I have kept 0.16 L1, this also I kept 0.16 L1. Okay, fine. So this is about midspan, and these are the two end support and continuous support about the bottom. Now for shear in ductile beam, obviously 2D. In non-ductile beam also I am providing up to 2D. If you see here, so up to 2D distance we need to provide the closely spaced stirrups. So that's why I kept it as 2D in both ductile and non-ductile case. I'll just click on OK. I think I have already discussed this. Now I'm just messing up again. Please pardon me for this. Now if I go to settings, and you can say detailed drawing settings, we have already done this. Still, let us check again. Effective span for curtailment, top and bottom. So effective span for curtailment, top and bottom. If I go to SP34, the effective span for curtailment, okay, top and bottom. For bottom, it is considering effective span. If you see the values, ln/4, so it is from face of the column. Okay, so earlier we have selected I can say center to center. Now I think I will select clear span, because this is the ductile design criteria. Earlier we have seen as per IS456 criteria. Okay, that means non-ductile criteria. So just let me remember the page number. It is page number 199. Earlier what we have done, if you go to the beam design, sorry, beam detailing, yes, so earlier we have done this one. You can see the effective span was from center to center for the bottom, and all these values L1, 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 you can see it is about the center to center effective span. Now in case of ductile design criteria, it is 199. Okay, 199. Thankfully I remember the page number. Now it is considering every value depending on the clear span. Okay, every value depending on the clear span. You can see ln/4. So what I will do here, I will now take it as clear span for both top and bottom. Fine. Then provide curtailment from. So if you see here, provide curtailment from this L1 or this A, it is from face of support. Correct. Here also it is face of support. So for top and bottom, both cases I will go to now face of support, support face. Okay, so it is fine. Now then we have make curtailment from. Okay, provide curtailment from face and support face. Then mark curtailment from. Okay, from where you need to mark the curtailment. I will provide support face only. Okay, because I don't think there is anything from center in this case. Everything is from face of support only. Correct. There is one ambiguity that we will be facing about this extra bottom if required. I don't think in ductile cases we will get this kind of detailing, like one bar like this. It will be continued only, like one bar like this, and again another center bar, and again another curtailment bar. No, if it is required, it will provide throughout, and extra end bars will be providing. Correct. So there is not an issue this much. But what I am concerned about, if you see here, as earlier we have seen this curtailment actually from center of the column. Now we have provided the ask the software to provide curtailment from the face of the column. So this thing also will be reduced. Correct. But as in the ductile criteria, this particular thing may not be coming, because it will provide a throughout reinforcement for the general case and extra bottom and top for the ductile criteria. So it will be resolved by this case as of I hope. So we will see when we will be doing the detailing part. Now let us go with this only. So all from support face. Mark span from support face as of now, and mark beam span. Okay, fine. Mark unique sections. Curtailment round off. Curtailment round off, you can go for I want it is as 25. Okay, it is a good number, multiples of 25. Fine, I'll click on OK. So we have done the detailing and drawing settings. Now I will go to preferred bar spacing. We have already provided this actually. Okay, we have already provided this. In 300 mm width, how many bars you need to provide? Okay, so I have kept it as 3 bars, and spacing between the bars we are getting 100 mm. It is, sorry, spacing between the bars, if the bar size is less than 16 mm, then it will be 100 mm. Bar size is greater than or equal to 20 mm, so you will be getting around 95 mm spacing, so it is okay, no problem. Provide 2 bars, okay, wherever there is no moment, but still we need to provide at least 2 bars for the bending moments, which we have seen in the code. Now I will go to basic load cases. Earlier we have selected this dead load and live load. Now we will be selecting the seismic load also. So I will just make it as EQX, 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 and this model is imported from StatPro. So for your understanding, Stat is having a plan, you can say axis as X and Z. So what you can do, you can select here X and Z only. This is just for the name purpose, okay? This is just for the name purpose. This X and Z, it is for the name purpose. If you are importing from, you can say E-tabs, so in that case what you can do, you can, rather selecting it as Z, you can select it as Y. Okay, so I'll just click on OK. You may ask about the vertical acceleration also. If we have vertical acceleration, then will it create the combination accordingly, because this will be used for the combination purpose also. Obviously when you have vertical case, then it may not be creating the you can say vertical combinations properly, because there is no direction connected to these names actually. Okay, these are just names, so no direction connected to these names, so it may not be creating that, you can say, vertical combinations properly. Or if you have some 30% rule in case of orthogonal, non-orthogonal column, so in that case you have to create the load combinations in the model itself, in the analytical model itself, and then from the analysis you can import it. I will show you just now. I'll click on OK. Sorry, I have not, sorry, what I have done, I have not taken the load cases to the list. Let me do it here again. EQX, EQX, EQZ, EQZ, and EQZ. I will select this. I will take it to the load list. I'll click on OK. Now we have only plan directional seismic force, so I will add it from the template. But if you are adding it from the template, and if you are adding as per, you can say, the regular structure, so it may not be creating the non-orthogonal cases of load combination properly. In irregular structure, maybe it will create that 30% rule, but I'm not sure actually. So it is better to import from analysis model, so that whatever load combination you have made, using those only, the software will be performing the design calculation. We will check it later. Okay, we will see in the later case whether this irregular structure, it is giving this 30% rule or for vertical and non-orthogonal cases. Okay, so now I will select this for regular structure, as I don't have any load combination in the analysis model. So all the regular combinations will be created as per IS456 and IS13920, sorry, IS1893 criteria. Fine, then I will click on OK. So almost all the settings we have done, and now I will perform the design. I'll click on this auto design. Okay, so the design is performed, and you can see in the mid span, bottom mid, mostly they have given throughout reinforcement only. Okay, so okay, fine. Now as per the best fit criteria, maybe it has provided, so we will see it later. Now we will go to report and we will understand the design calculation. So let us click on this design calculation for, suppose, group 1, which is consist of 3 beams, B1, B2 and B3, and I'll click on OK. So this is my design calculation, detailed design calculation given by RCDC. So obviously the general information, as we have seen earlier, the symbols and their definitions, we will see this whenever it is required. You can refer actually whatever symbols they have used. So if it is required for you to understand, you can refer from this. Then we have code references. We have 13920 references and IS456 references. If you see PT max 6.2.2, PT mean 6.2.1, we have already seen. AST minimum, the criteria of 6.2.3 and 6.2.4, and the shear spacing calculation, sorry, as we shear spacing, shear capacity and coupling beam. We will see this later. Okay, we will see this when understanding this calculation. So the group name is G1 and we will be checking the beam number, which is B1. Analysis reference member, so as it is a STAD model, so it is at 3 meter level and the STAD element number is 57. Beam length is 6 meter, 6000 mm, width is 300 mm and depth is 500 mm, which is provided in the analytical model. Effective depth, small d, it is 445 mm. So I have discussed it earlier also, and I have given the list also how RCDC is calculating the effective depth. So basically when it is greater than 400 mm, it will consider 2 layer of reinforcement at bottom and top, wherever you are finding the tension reinforcement. It will consider the 2 layers. First, it will provide the maximum bar size that we have provided in the design detailing result, and the minimum bar size in the next layer. Okay, so if you see here in this design calculation, so we have a bar. Now it is coming 445, right? So we have a bar around 16 dia bar here. Okay, also 20 dia bar here. So maybe in this case it will be reduced. Let me check. Okay, so if I use this 16 dia bar, okay, the provided minimum reinforcement dia, which is 16 dia. So in this case, we have the stirrup, we have the main bar, clear cover is 25, main bar is of 8 mm, stirrup is of 8 mm dia, and this main bar, suppose first let us check with 16 mm whether it is considering the minimum one or maximum one. 16 mm first layer, so in that case the second layer will be of 12 mm dia, though it is not provided, but it will be considering the next minimum dia bar. So if I calculate the effective depth, D equal to 500 minus 25 minus 8 minus, I'm finding from here, okay, 25. So effective depth is this one. This is the effective cover. So effective depth will be the total depth minus this cover. So this cover is 25 minus 8 minus 16 minus 12/2. Okay, so how much we are getting? 500 minus 25 minus 8 minus 16 minus 6, we are getting 445. Okay, so what it has done, it has taken the minimum reinforcement bar provided in the detailing, okay, in the first layer, and then it has calculated the other layer with the next minimum bar, and it has given the effective depth. We have seen this earlier also, now also we have calculated, but though in the top it has provided 20 mm dia bar also, so it has not taken the first layer as 20 mm, but it has taken the first layer as 16 mm only. I don't know whether it has done some average or not. 16 plus 20 divided by 2, so something around like this. No, it has taken the minimum dia bar only. Minimum dia bar provided 16 and its next minimum dia in the next layer. So okay, we can justify this effective depth as 445 as we have different bar dias here. Fine. So design code, then type of design, ductile design, grade of concrete, grade of steel, you can say the clear cover, and the Young's modulus of steel, which is 2 into 10 power 5. Critical load combination, so in different locations, beam bottom and beam top, we have different critical load combinations. The maximum we are getting here, you can see the bending moment, which is 139.76, and it is at the top. The torsion we are getting 0.39. So let us check only this section. If you understand the calculation, one section, all the sections are different, same amount. So here if you see the load combination, it is load combination number 16. Fine, we will see what it is. this is my mu, this is my tu, and this is my mtu, this moment due to torsion. So how to find this moment due to torsion? This moment due to torsion, if you remember, the formula is T into 1 plus D by B by 1.7 as per IS13920. Correct. So my torsion is 0.39 multiplied by 1 plus D is 500 mm, B is 300 mm divided by 1.7. How much we are getting? I have already discussed this in the previous section also, but again I am doing it so that you don't, you can say, it doesn't create any, I can say, doubt in you. So 1 plus 0.5 by 0.3 divided by 1.7. okay, so it is around 0.6117. we are getting a value of 0.61. you can see it is 0.61. then we have the MDU, just refer these values actually. Then we have the design moment, which is 140.37. so this is actually this 139.76 plus 0.61, so we are getting 140.37 around. okay, let me see, 139.76 plus 0.61. you can see 140.37 is my design moment, so it is my MDU. then we have the moment capacity. so if you see here, mu limit in kilonewton meter, how will we be finding it? so if you remember, in the previous session we found, as per, let me just delete all this, so as per NX G of IS456, we had the formula for mu limit. okay, mu limit, and putting the value of xu by d for Fe 500, we found that mu limiting is equal to 0.133. let me write it the below. so we found it is 0.133 multiplied by FCK into B into D square. okay, so if I just again calculate this, it will be the same value that we have seen in the previous session. so 0.133 multiplied by 25 multiplied by 300 multiplied by 445, this is the effective depth, so 445 square. so it is around, you can see, 197.529. so we can say this is 198 kilonewton meter. okay, I have just converted into, this is in Newton actually. I multiplied this with 10 power 6. okay, sorry, I divided it by 10 power 6, so it will be 10 power minus 6. okay, and then we got this value of 198, correct? so now, so this is this 2.363 R, this is nothing but the mu by BD square. okay, fine. then we have PT minimum percentage of reinforcement, you can see 0.24 as we have provided. PT calculated at this section, it is 0.621. okay, 0.621% PT calculated. PC calculated for compression reinforcement, there is no compression reinforcement, so calculated compression reinforcement is 0. PT provided, okay, tension reinforcement provided, it is 0.706 as per this criteria. okay, so 320 bar, if you see, let us check. okay, AST by BD will do. so 320 means 3 into 314 okay, multiplied by whole section, so 0.3 multiplied by 0.5, it is around 6.28. If I do it 0.445, I'm getting, yes, you can see 7.06. okay, you just have to multiply this value with 100, then you will see this is the, sorry, I have done a mistake. If I just do it here like this, 2 into 314 divided by AST by BD. B is 300, D is effective death 445 multiplied by 100. So we are getting a value of what I have done mistake. Okay, sorry, not 2. Here you can see I have done mistake here. It is actually 3 bars of 20 dia. So it is around 0.706. okay, 0.706. As per IS13920 criteria, actually the gross area should be taken, but here in RCDC it is taking the effective area, though it is not an issue because it is providing a bit higher value, but so we're in the conservative side, so we can ignore it. Then like in IS 456 we do consider I can say effective area only, so okay, we can you can say consider this. Then we have AST calculated. So the calculated AST is 828.49 at the top, and AST provided at the top is 942.48. Now let me go to this bottom of this right. So calculated AST is 414.69. okay, and AST provided it is 603.18. Why? Can you tell me why it is 603.18? So if we see, we can check the different criteria now, because at this section the moment is 0. okay, then why this much reinforcement is provided? So if I see this first criteria, half of the top reinforcement provided, so half of 942.48 divided by 2, so we are getting 471.24. this is one criteria. Another criteria is 1/4 of, okay, I will do it like this, 1/4 of the top reinforcement, which is 942.48. so we are getting a 235. so obviously 471 is the governing criteria in this case, and 471, if we provide 16 mm dia bar, 216 mm dia bar means 400 and something. You see 2 into 201, so it is 402. if we do 3 dia bars, it is 603. so we cannot provide 2 bars of 16 dia, so that it has provided 3 bars of 16 dia. okay, because we need to have at least half of this value. okay, so half of this, half into this 942.48. okay, whatever we are getting this value, this should be greater or equal to this value, correct? so it is matching, it is meeting the criteria, and so finally we are getting the reinforcements for these sections, correct? Fine. Next, if we see the shear design, so at this end only let us check shear design. PT provided is 0.706%. analysis shear, it is VU, it is 95.33. torsion we are getting 0.39. so so this is my TU. Now if I find the VTU, means shear due to torsion, what is the formula? I think it is 1.6 times. If I go to IS456, so you can see here it is 1.6 times T by B. So if I do it here, it is equal to 1.6 times T by B. So how much it will be? 1.6 times torsion is 0.39 and beam is width of beam is 0.3. So it is 1. What we are doing, 0.39 and 0.3. Let us see how much we are getting. Uh, 0.39 by 0.3. Okay, something around 1 point something will come, multiplied by 1.6, and we are getting a value of 2.08. Okay, so it is giving 2.07. Fine, we can consider this. Sorry, it will not be, it will be 0.39. so suddenly we are getting 2.08, so we can take 2.07. it's fine. So VUT, okay, so it is the final shear, which is 95.33 plus 2.07, so we are getting 97.4, around 97.4. okay, now V dead load plus live load. Okay, this V dead load plus live load means shear due to 1.2 times dead load plus 1.2 times live load. Why it is required? Why it is required? To find out the, if you see here, IS13920. So when we'll be doing that shear design, you can see the code has asked us to consider this beam as a simply supported, and this shear, equilibrium shear, we need to consider. So the formula is V dead load plus live load plus minus 1.4 moment capacities, addition of moment capacities divided by span. Okay, so if you see here, we have V dead load plus live load, which is due to the with the 1.2 factor. And why 1.2 factor? Because next it will be combining with the seismic force. So like this, hogging moment capacity, it has given 156.55. sagging moment capacity, it has given 106.16. correct. Sway right to left. So my beam is like this. Okay, sway, it has written sway to right. Okay, sway to right means we are getting a value of like this. So in this case, MS MH. Okay, so if we do these values, how do you know how to find these values? 156.55, 106.16. so this is actually the same moment capacity that we find. Let me show you. You can find out using this formulas in NXG. actually NXC, I will go to NXG. Yes, so you can use this formula, mu is equal to 0.87 FY AST. You have the provided AST. If you put, then you will be getting this mu value. So for this I have created one Excel sheet. Suppose I will take this end, and this end we have provided 320 dia bar. Provided reinforcement is 320 at the top and bottom is 360. So if I just put it here, suppose I will give 300 and 500, 6000 is my length, M20 grade, 500 grade, 415 and 25 mm clear cover. At the start, I am not considering start. Suppose this is the end. So end of the beam, we have provided top. So we have provided 20 mm dia bar, 3 numbers. There is no second layer. Okay, stirrup dia is 8 mm. and effective depth it is considering 457, so it is around 161.60. Are we getting the same value here? Are we getting the same value here where it is? So it is considering 156.55 for hogging moment for 320 mm diameter. In our case we are getting 360. Oh, okay, actually because of this thing, actually I have given this as per the provided formula. So what I will do, here I will change it manually. Suppose I have selected actually to find out the actual effective depth, but as RCDC is considering this as 2 layers when in case of greater than 400 mm depth, so I will just provided it manually. Suppose 445, I'll press enter. So now you can see it is matching 156.68. okay, conservatively it is doing, so it is 156.55, around the similar value I am getting. And at the bottom we have provided 16 mm diameter 3, and I will make it as 445, so it is around 106.21. so you can see here, using this formula we are getting 106.16, around the same value. Okay, so this kind of sheet you can create to get the actual one. Actually RCDC is doing one thing, to check it you can say use this sheet also, this kind of sheet also, like creating. So I have just used this formula here, mu is equal to 0.87 Fy AST d multiplied by 1 minus AST Fy by BD FCK. okay, using this I have found out the you can say moment capacity of top and bottom in kilonewton meter. Correct. This thing you can say create formula also, like I have created here. If you see, I have a created formula using this provided reinforcement, but RCDC is doing a different way. So you may have, if you want to check the result from RCDC, you have to put it manually. Okay, so we have checked, we are getting the same value, correct. Then we have sway right to left. So suppose this is my beam, okay, and my sway is happening, sway is happening along right direction, okay, towards the right direction. So it will be something like this. So here we will get sagging, here we will get hogging. So the formula was Vd plus L plus minus 1.4 times. So now it will be moment capacity sagging, moment capacity hogging divided by LAB. Okay, so obviously if we do minus, it will be reducing, so I'll do only the plus one so that you can check. My dead load plus live load, here it is 68.53, so 68.53 plus 1.4 times moment capacity sagging 106.16 plus moment capacity hogging, we are getting 156.55. so 156.55, sorry, not this value, this value will be used because this is the start and this is the end. I have by mistake I have checked this actually. So start, what we have provided 316 diabar. So for that, what is the moment capacity? This will be used, not this one. Okay, not this bottom reinforcement of the same section. For the start it will be bottom, for the end it will be top. So moment capacity sagging at the start, moment capacity hogging at the end. Okay, so 156. Okay, so with the sheet what we have calculated is correct only, as the provided reinforcement is same. But remember, whenever you are checking like this, so first you will check like this, then again from for other direction, end will be sagging and start will be hogging. So like that you need to check, correct? So divided by my 6 meter. So how much we are getting? Please do correct the mistakes what I have just told actually. Okay, I was checking this moment capacity, which is exactly the same section. It will not be like this. When sway will be happening like this, moment capacity which will be adding here is where we are getting sagging. That moment capacity we need to add. So here start, at the start we are getting sagging, so we will add the moment capacity of start, sagging moment capacity of start point, and at the end we are getting hogging, so hogging moment capacity at the end point. Okay, so same value, so no issue, calculation will not change, but you need to keep it in mind. So let us calculate 68.53 plus 1.4 times 106.16 plus 156.55 divided by 6. So around 37. I have done mistake here. I have done any mistake? Yeah, I have done a mistake. Whatever unexpected result when I'm getting, obviously you will be sure that we get. Okay, so 129.829. 129.829. What we got here? We use sway. So we are getting a value of 134.21. Sway right, sway left. Okay, the same value only. 134.21 it is writing. Sway right, sway left. Same value we are having. Why 134? Is it calculating? We done any mistake? We are getting 129. Okay, I think 𝐶𝐴𝑠𝑝AN it is considering. Now I didn't remember what was the column size I have taken. Most probably it is considering the 𝐶𝐴𝑠𝑝AN actually. I don't have a data for 𝐶𝐴𝑠𝑝AN. Let me check. Okay, let us keep it here. Let me check what was the 𝐶𝐴𝑠𝑝AN. Let me open the model, because whenever we are verifying any data, if the answer is not closer, sometimes it is very hard to, you can say, digest these things. Okay, so let me see. Okay, I need to open this. Okay, so what is the column size I have taken? I have taken a column size of 400, 500. Okay, and I am talking about the member number 57 at 3 meter level. Okay, let me select the member number 57, beam 57 from here. Okay, and let us isolate these columns also, this beam and this column. Okay, view, and if I see control 2. Okay, so the column is oriented this is the beam most probably. I've just lost it. 1 second. Control 0, 57. Yeah. So if I just click on Control 2, you can see column is oriented along this direction. Okay, so we have the column size 400, 400. So this, let me keep it like this only. So this is 400 along x direction. This is also 400 along x direction. If I find out the clear span, it will be center to center span, effective span minus 400, total 400, 200, half for this column, half for this column. So if I just do it, 6000 minus 400, so it will be 5.6. so I will do it as 5.6. I'll go back to the here and I will take 5.6. so am I getting? Yes. Now if you see, I'm getting the exact value of 134.21. okay, 134 point. So rather it will be 5.6 actually. So I will write it here, clear spacing. Okay, or clear span I will write. Sorry. It will be clear span. Okay, so we are getting a value of 134.21, which is correct. So this is my equilibrium shear. Now we need to compare the shear, which is VUT 97.4, and the equilibrium shear. Whichever is maximum, we will be considering that as our analysis shear. So now here also for both directions sway left to right or sway right to left in both cases. So one thing you can see, plus and minus you will do actually. Okay, sway right and sway left. So for plus and minus you will be getting, and so obviously we're getting 134.21 for the VU sway. This is the maximum value. Among these two, the shear that we'll be using for design, it is 134.21. Now the similar thing, same as IS456 design, tau V will be finding out, which is VU by BD. VU will be used this 134.21, tau C from table 19. Okay, VC. So in as per IS13920 criteria for shear design, VC cannot be taken. Shear capacity of concrete cannot be taken into account. If you go to IS13920, I think we have already in my ETABS and stat course we have already discussed this. Let me show you here also if it is there. Let me see where it is. Okay, here it will be only vertical links. Okay, here you can see in the calculation of design shear force capacity of RC beams, contributions of following shall not be considered: bent up bars, inclined links, and concrete in RC section. So contribution of concrete in shear capacity cannot be considered. So that's why VC is written as 0. So whatever shear you have got, that will be your final VU. For each you will be finding out the you can say shear reinforcement. Actually earlier what we have done, we have found out VU is equal to VC plus VS. We found out the VC, then we deducted the VC, and finally we got VS, and for this we found out the shear reinforcement. Here this VU directly will be the VS there will be no reduction, and you will be finding out the shear reinforcement providing using the formula. If you remember, I think it is 0.87 Fy AST AS into D by SV, something like this. VUS equal to, correct, where this Fy will be considered as 415 as per IS456. Okay, and this is the spacing. So anything this for 1 meter you will be finding out. Okay, this I have already discussed, so I am not going to discuss this again. ASB torsion, we all know, this is for the torsion. So the provided reinforcement is now 8 mm dia bar with 2-legged. If you provide this, okay, so ASB torsion already discussed actually. Let me show you again. ASB torsion will be calculated using where it is, sorry, torsion, I need to find out, Control F, torsion, I think page number 75, correct, or 85. It is not there. Page number 80 or something. Let's see. Yes, page number 75 if you see. So this is the formula to find out the shear reinforcement when you have torsion. Okay, transverse reinforcement when you have torsion. So this is the formula used for this. So provided for torsion, it is this one. Okay, that means the 2-legged stirrup with the spacing that we have considered. I will come to the spacing part again. So this is the provided. ASB required. So it is as per this criteria that I have just shown, 0.87 Fy AST into D by SV. SV calculated and SV provided. Okay, so now let us see how this SV is found out. So first, IS456 criteria, 0.75 into effective depth or 300 mm. So we got these two. Here the lesser one is 300. So from here we will take 300. For torsion, we know center to center distance between, suppose this is my stirrup. So this is my X1 and this is my Y1. So when you have torsion, in that case either X1 or X1 plus Y1 by 4, whichever is less, that will be your spacing. So in two cases we have 1 260, 1 175. So now among these two we have 175. Okay, fine. Now we will find the ductile criteria. First one is D by 4, we are getting 111. Then we have 6 into longitudinal bar dia. So 6 into longitudinal bar dia, how it is getting 75 here? How much? 75. 6 into 16, 96. 6 into 12, 72. Okay, 12 we will not consider. In the top we have provided 620 dia bar. So 6 into 20 is equal to 120. So why 75 considered? Because we have provided in the detailing criteria that minimum spacing will be 75. So either we are getting a higher by dia only, so but still it is providing 75 mm, sorry, higher spacing only, but it is providing 75 mm as per the provided guide. If it is less than this value, then it will be provided the lesser value. Okay, then another spacing which is 100 mm. So whichever is less. So among this all these values we found the 75 mm less at the end. So that's why 75 mm are provided at the end. In between, at the mid span, when it is found out, so effective depth, you can say first one is not side span reinforcement. So at the mid span, what is the criteria? It should not be greater than D by 2. Okay, so if you see mid section D by 2, so 222 is coming, it has provided 150. How it is provided? This 25 mm we have provided this 25 mm, you can say, should be the I just forgot the term actually, sorry. If I provided here, if you see here, okay, so a spacing round off we have provided 25 mm, so the required one is 222 and provided is 150 mm spacing. Okay, 150 mm spacing in the mid span and 75 mm spacing at the end span. So as per the IS456 and IS13920. Then as we are designing as per torsion, with the torsion, and the beam depth is more than 450, I can say, let me see what was the criteria. I think 400 or 450. Torsion, yes, here. Okay, so remember exceeds 450 mm, we have 500 mm depth. So in that case, we need to provide the side face reinforcement as per this clause 26.5.1.7. Okay, so side face reinforcement as per this criteria, which is 26.5.1.3. So 0.1% and should not be the spacing criteria should not be greater than 300 mm. So how it is provided: beam width 300 mm, depth 500 mm, torsion value which is greater than 0, so there is torsion. Beam depth is obviously beam depth is not greater than 750. It should be written as 450 actually. Two cases are there: either beam depth is 750 or torsion is greater than 0. So in our case, torsion is greater than 0, so side face reinforcement will be provided, and spacing between the side face reinforcement is 150 mm. So 112 mm dia bar. Actually, spacing between the bars should not be 300 mm. So we have already provided these bars. Okay, so one bar is provided here. This is 500 mm. If we even see the effective depth is 450, suppose. So 500 also, if I consider, it should be at least 250. Obviously, it will be less than 250, but I am considering, suppose I am providing at the very edge, so it will be 250 and 250. So the distance between the bars are less than 300 mm, so it is okay. Okay, fine. So 112 mm dia bar provided at the side face reinforcement for the torsion. Fine. So this is how the ductile design is being performed in RCDC, and as per our calculations, all these things are totally okay. Okay, some values point difference we got, but that's fine. Effective depth, okay, it is taking some effective depth considering some minimum reinforcement, not the very actual one for every section. You can do it using this kind of, by making this kind of sheet which I have provided. So those who are enrolled in the course, obviously I'll be providing this sheet, you can download and you can use it. So provided reinforcement, provided stirrup, accordingly it will calculate the effective depth of every section, and it will calculate the moment capacity, exact moment capacity. Okay, and then you have to provide this data, you can see, which is the 1.2 dead load plus 1.2 live load, but unfactored in terms of unfactored load, which you'll be providing from the stat actually. So, and then what is the design shear, that means the analysis shear that you are getting at the start and end of the beam, and what are the reinforcement that you are going to provide. So if you just see this sheet, it will be very easy sheet, you can automatically understand once you know the calculation. Right, I'll share this sheet. Those who are into the course, you can easily use it. So I hope the ductile design of beams as per IS456 and IS13920 criteria in RCDC is clear to all of you. Okay, so in our next session, what we will do, we will see the detailing. What we will see the drawings actually, which is generated by the by RCDC, and we will see how these drawings we need to, like, what are the modifications we need to do in the drawings before sending those into the site. Okay, so this is it for today's session. If you have any doubt, you can always write me in the chat box. And this video, as this videos will be always this video will be available in the YouTube. This particular video will be available in the YouTube. So those who are watching this video in the YouTube, Basically, this is a part of one of our course which is on RCDC as per Indian code. So if you want to be a part of this particular course, you can find the link in the description box. You can have a look on the content. The first lecture is open to all, so where I have explained the content, and this kind of detailed calculation we will be checking in every cases, in case of column also, in case of slab also, and we will see the detailing criteria also and detailing drawing also. Okay, so you can have a look on the course curriculum, and if you find that it is useful to you, you can have a try to this particular course also if required. Okay, if you like it, please share this video with your colleagues also, so that everyone can benefit it. Thank you, and see you in the next lecture.